Energy is a conservable quantity. Energy is a conserved property of nature, and it's neither created nor destroyed. So that means you'll neither gain, create, or destroy, lose energy. It just flip-flops from one form to another. And the basic assumption that holds true is that if a system is closed, it neither gains nor loses energy, and the net or the total amount will stay the same. Energy can only move from, the only way energy can move in or out of a system is if it's added or taken away. So let's look at look at these people on a roller coaster enjoying conservation of energy. We start off with some initial condition and we end up with the final condition. The total amount of energy that we start off with is what we end up with in the end. And that's important. So we could say energy initial is equal to energy final. So E is the initial, E prime, that symbol prime just denotes that it's the final condition. And in essence, this is the rule that governs the entire universe. It's so beautiful. So beautiful. What is energy? It's extremely difficult to explain. You're hearing energy or you're observing energy in my voice right now. You're probably looking at a computer monitor or a television. You're observing electromagnetic energy. That's a form of energy. Or your heater turned on, or your air conditioning. We're adding and removing energy to a physical system with those devices, heating and air conditioning. What energy is extremely difficult to define. However, even though it's hard to define, it's extremely useful when we're making measurements or predictions in physics. Hey, this concept of energy is almost like a crystal ball. It's very mysterious, but we can use this crystal ball, let's say, to look into the future. Recently, in the previous slide, we defined conservation of energy. If we call the amount of energy that we start off with as being E prime or E naught, the initial form, and what we end up with as being E sub F, the final energy, again we say that what we start off with, the initial energy, is equivalent to the final energy. It turns out that there are only two ways to change energy in a physical system. One is heat and the other one is work. If we define positive work with an increase in energy, we end up with an equation that looks like this. And I'll explain what this means. The energy, what you start off with, will be equal to the energy that you end up with, only in cases where this thing called work, and we'll define work in a moment, is non-existent, when it's zero. So if work is zero, what you start off with is what you end up with. But let's say you do work on an object. We'll reveal the work. If work is done on an object, that number will not be zero, and the object will gain energy. Let's look at an example. Just say, for example, you start off with 10 units, 10 joules of energy. And let's say no work is done. 0 joules of work are done. In the end, what you start off with, 10 plus 0, will be what you end up with, 10 joules. If this work is not 0, let's just change it. Let's say that work is 2 joules. The new answer would be 12 joules. This object would have started off with 10 joules. If 2 units of work are done, it gains 2 joules and you end up with 12. But they're still equal. What you start off with, energy plus work, is what you end up with. Again, a very beautiful concept. Work is the ability to cause change. If you look at these gentlemen pushing on the aircraft, it's easy to see that a force will be acting in the direction that they push. It's going to act on the airplane. And if that airplane moves, and let's assume it's moving in the direction that the force is applied through some distance, work is going to be done. Work can be done on a system when an external force, the red vector is the force, is not part of the system. Where does that work come from? Or excuse me, where does the force come from? It comes from the people. An external force coming from the people is acting on the airplane, it moves, and work is done. So these folks are essentially doing work on the plane. The airplane will change its motion because work is being done. We can define work mathematically. Work, by definition, W is work, I'll write this in words, is equal to the product of force and distance or displacement. Displacement we'll use in this case. So work is force times displacement. W is F times D. And we can use this equation in order to predict if work is done. Now, it says D parallel. Work will only be done on an object when it moves in the direction that the force is applied or the opposite direction. So it could be parallel or anti-parallel, and we'll take a look at that in the next slide. In this case, this acrobat is in a state of equilibrium. He's not moving. Since there's no distance traveled or displacement of this person, there's no work being done. Let's write the equation down. We'll jot it. Work is force times displacement. And since the displacement is 0, if I were to put a 0 on one side of the equation, automatically the other side is 0, so there's no work being done. This is extra, and this is not related, but let's free body diagram this guy. What's pulling down on him? What force is acting downward on this gentleman? That's right, it's gravity, and that force will be mg. Now, if the only force acting on this guy were mg, he would free fall down. He's not moving. He's neither moving up nor down. So that downward force must also be accompanied by an upward force. And that is the plank that he's standing on is pushing up on both feet. Take a second to see if you can remember which his force is, which force this is. That's right, it's the normal force. And since the normal forces are balanced, there's no net force. And since there's no movement, there's no displacement, the work done on this guy is nothing. Alright, an example of a case where work is done on an object. Is there a force? Yes, there is a force. So that force is not 0. And it's moving. Just imagine this object is moving to your right. So the displacement is not 0. There is a displacement. We'll put a D here. If the force and the distance are not 0, then there's work being done. The sign of the work on this case is positive. When the force acts in the direction of the displacement, positive work will be done. And the work is greater than 0. So it might be positive 1, positive 2, etc. and so on. So work is being done. Now since the mass is experiencing an unbalanced force, acceleration will occur. If we were to draw velocity vectors for this object, let's give it some non-zero velocity to the right in the beginning. I'll call that the initial speed, v0, and then sometime later, because an unbalanced force is acting on it, time is going by. 1 Mississippi, 2 Mississippi, 3, and so on. When it gets to this point on the table, its velocity would have increased. And if you see it's going slow, here it's going fast. Work is the ability to cause change. It accelerates. And this object will change its velocity. Not only is it going to have work done on it, it will change. It's another form of energy. It's kinetic energy. It's the energy of motion. So it starts off slow, ends up going fast. Its motion changes. Big picture. Next slide. This is an unusual one. So we'll use our imagination here. Just imagine that this object, and we'll draw velocity vectors on this in a moment. Just imagine, does this object have a force acting on it? The answer is yes. So there is a force. It's unbalanced. And there is a displacement. So there's work being done. Definitely there's work being done. In this case, the work is negative. When the force vector and displacement vector oppose each other, or they're anti-parallel, they point in opposite directions, the work done is indeed negative. And if this object were, let's give it a velocity vector to the right, and I'll make this one large, I'll call this V0, and then sometime later it's going with some VF, it would have slowed down. Think of a force that would make this slow down. That's right, friction. So just imagine this is sliding across this rough surface and it's moving from the left to the right. The frictional force would be opposing motion, and it would go from a large velocity to a small velocity. This is negative work. Again, acceleration occurs because there's an unbalanced force and work is done. So the work is negative in this case.
Zero work. If the object moves in the direction perpendicular to the direction of the force, here we have a force going up, the normal force, and here the object is moving to the right. And in this case, the force and displacement are at right angles or perpendicular or make a 90-degree angle. The work done here is zero. The energy of the system is unchanged. No acceleration occurs due to the fact that no component of force acts in the direction of displacement. In this case, no work is done by the normal force or the force of gravity.
Now, we have a quantitative understanding of what work is. And we've defined the equation for work. It's the product of force times displacement. Work is done when displacement is in the direction with or against the force. But we can define the units for work. And work is force, which is newtons, times displacement, which is meters. So work could be measured in Newton meters. That's 1 unit. Another way of writing this is kilogram meter squared per second squared. I can define that. It's going to take a second. Newtons are kilograms. Newtons are mass times acceleration. Kilograms times meters per second squared. So that is a Newton times a meter. So we end up with kilograms times meters divided by second squared. And it gives us the fundamental units for work. But most people will refer to work in joules, named after, in honor of James Joule, who made critical contributions in the concept of energy, specifically thermal physics, and we named the unit of energy in his honor. What an honor. Just like we named the unit of force after Newton. So work could be measured in joules, Newton meters, or kilogram meters squared per second squared. It's most intuitive to say that work is done in joules or Newton meters. Very rarely will you say, oh yes, so-and-so did 65 units, 65 kilogram meters squared per second squared units of work on this. But most of these, all of these units can be broken down into fundamental units. And interesting, mechanics deals primarily with mass, length, and time. You can do anything with those 3 quantities. So beautiful. Again, here's a picture of James Joule himself. And again, this is a statement of conservation of energy. Objects will, when no work is done, the initial energy and final energy will be equivalent. Energy is measured in joules, work is measured in joules, and energy is measured in joules. If there is work done, your final energy goes up. If the work is positive, the final energy goes up. If the work is negative, the energy will go down, just like we saw in the previous slides.